All right, question 3. Okay, I already started this one here. I misspoke, so I wanted to go ahead and redo it. So we have a sled. Its mass is m, which we don't know, and it is given a kick on a frozen pond. The kick imparts an initial speed to the sled, 2 meters per second. And this one has friction. There's a coefficient of kinetic friction between the sled. That's our mu of 0.1. Use energy considerations to find the distance the sled moved before it came to a stop. So I know that you could use kinematics on this and determine the acceleration or the deceleration of the sled, and from there you could figure out what the change in x is, but I want you to use energy, being this is the energy chapter. Okay, so if I draw out a picture, okay, of our sled, it should look something to this effect. All right, we're going to have the sled starting off here with an initial velocity of 2 meters per second. It will transverse a distance. I'm going to call it delta r, okay, in the x direction or whichever direction this is. I'm going to call it delta r until eventually the sled comes to a stop. Vf is 0. The ice gives us our mu, 0.1. And to do this, we should look at work. Being that there's friction, we can't use energy conservation, but we can use work because work is the change in energy. So let me look at the work lost. How much energy did we lose due to friction? Well, to do that, I'm going to use work. Work is equal to a force times a distance times cos theta. The force I want to use would be friction because that's what's lost. That's the amount of energy that's lost. Force of friction we know has a nice equation of mu times the normal force. Change in r and the cosine of theta. So to find out the normal force, we can go back and we can draw a free body diagram, which I drew over here. So we can have a free body diagram on our sled, and we can see that the force of gravity is mg, and the normal force is pointing upward, and the friction force is, of course, pointing backward, slowing the sled down. If we sum up our forces, we can do that over here, sum up the forces in the y, we see that the sled is not bouncing up and down on the snow, it is simply sliding to a stop. Okay. And for that, we see then that Fn points up and Fg points down. So we would have Fn minus Fg. Being this is equal to 0, I can say that Fg is equal to Fn, and Fg I know is equal to mg, so Fn must then also equal mg. Okay. So plugging that in, I see then that mu is given as 0.1. The normal force is equal to mg, so I have m, which is unknown, times g, 9.8. We have the distance at transverse, delta r. That's what the question is asking. Find the distance the sled moved. So I'm looking for delta r, the distance there. And the cosine is always 180 degrees for friction. So it's moving along this line. Friction always points the other direction from that. So from there, we'll get a -1. So there's a few things I don't know. This is the amount of energy that is lost. Okay, we don't know that. I don't know the mass of the sled, but I'm looking for the change in r. So there's a few things I don't know. So we got to look and see where we're going to get this. Well, we ask ourselves, where did it come from? We just used up some energy. We lost some energy due to friction. Where did that energy come from that we were able to spend it? Okay, so we got to do a little accounting. That energy came from the kinetic energy falling from 2 meters per second down to 0 for the velocity. That's where we got the friction. It was moving, now it's not. Where did the energy go? Energy got burned up by friction, which is a non-conservative force. Okay, so we need to figure out how much energy was lost. Okay, and we can look at that by seeing what was done initially. So we initially just had kinetic energy. Okay, there was no potential for gravity. It was a horizontal sled, and there was no spring involved. So there's no other way it could come into it. It had to be kinetic energy that was lost. So for here, we look at the change in kinetic energy. Okay, we start off with 1/2 mv final minus 1/2 mv initial. Well, the final, the sled come to a stop. So the sled is 0. So the final goes away, leaving just -1/2 mvi, or -1/2 mvi squared. Okay. From there, we can take and plug this straight into the amount of energy that was lost. This is what was lost, the kinetic energy. Take this negative 1/2 mvi squared and plug it straight into what was lost. So I'll get negative 1/2 mv initial squared is equal to, and then this I'm just copying from up here. So 0.1 times m times 9.8 times the change in r times the cosine of 180. And we'll see that that also will cancel the m's because they occur in both sides. Now I'm looking for the change in r. The only thing I need to plug in is vi, which was given in the problem. So we can solve this. So let's see, I'll have a negative 1/2 of 2 squared. So this will end up being a 4, and then when I take the half, it'll drop back down to a 2. That's equal to 0.1. M is canceled, so that'll be a 9.8. This is all equal to the change in r, and cosine of 180 is just a negative 1. All right, so plugging in, half of 2 squared gives me a negative 2, but a negative here and a negative here will actually cancel, so I'm going to go with a 2. 0.1 of this turns this into a 0.98 change in r. Okay, so hopefully that was okay with the math. Now all I have to do is just take 2 and divide by 0.98, which is just about 1. We end up with that the change in r is equal to 2 and then it's 2.04. We're just going to go ahead and just round that up to 2 meters. And that's our change in r, which matches our answer up here, 2 meters.